23, 69. Check if there is a valid partition for the array. Let's first try to understand the problem. So we are giving an array nums, so these nums will be just positive integers, and we need to check. So there are 3 conditions. So our target is to split the array into subcontinuous arrays. So for example, we can split this array to 4, 4. So the first, this 4, 4 means for the subarray, if it consists of exactly 2 equal elements, so for example 2 and 2 is good, so 4 and 4 is good. And next, we can have 3 elements, 3 continuous elements like 4, 5, and 6, or we can have 3 unique numbers like 4, 4, 4 or 5, 5, 5. And you should notice that if you have 1, 3, 5, it is not okay. So for the subarray, it can be something like a continuous array with the 3 elements, or 2 and 3 unique element like 2 fours or 3 fours. So according to this is a typical DP problem, and it is a linear DP problem. We can solve it by using DFS plus memorization. So let's just start coding. I'm going to prepare a variable n, would be length of the nums, and I'm going to prepare a class. Because this class is prepared for the DFS, because it is a DP problem, so I'm gonna use a class. So finally, I'm gonna return this DP as 0. I'm going to start from index 0. Now let me just start coding for the DFS part. So for the DFS, basically we need to check in which condition our index can go forward. So let's just copy this array to have a check. Let me copy it here. So for the first index, it is 0. We have to check. So if I plus 1. First of all, let's just check 2 integers. If there are 2 integers connected to each other, like the 4 and the next 4, we're gonna check if these 2 integers equal to each other. So if I plus 1 less than n, and nums I equals to nums I plus 1, so we can go for the DFS. And currently, we can put it inside a variable. So for example, it is the first. It is the first case, so it's going to be the DFS I plus 2. And secondly, if this I plus 2 less than n, so we're going to check 3 continuous integers like 4, 5, 6 or 4, 4, 4. It would be the second case. We're going to check this case. And nums I equals to nums I plus 1 and equals nums I plus 2. And it would be or, because there's another case. So let me just copy the code from here. So another case is nums I plus 1 equals to nums I plus 1. And here inside it's gonna be add nums I plus 1 equals to nums I plus 2. So that is all the conditions. If that is okay, we're gonna prepare a second case. It's gonna be DFS I plus 3. So finally, we're gonna return the first or second. If either case is okay, we're gonna just return either case. If either case is okay, we're gonna return true. So before that, we should prepare our first and second variable. So from the beginning, the first and second should always be false. So this means even if we didn't go for the DFS, from these areas, we're gonna return a false. If either of them, we can go forward, either of them return true. So finally, we're gonna return true. But how can we check that the final result should be true? We just need to check the index I. If this index equal to n, it means it can go to the end of the array. So this is the end of the array. It can just jump out of the array. So the next position is n. Here is n minus 1, and the next position is n. If it is I equal to n, so we're gonna return a true. Yeah. So this is the entire code. As you can see that it is not so difficult if you directly use the DFS plus memorization. Maybe you would to use tabularization, but that would be much more difficult than you expected. So for me, I would prefer to use this kind of DFS plus memorization for solving the linear DP problem, because it's gonna be quite easy. We just need to check all the conditions and find the edge cases to return a true or false. Now let me just run it to check. As you can see, it works. Now let me submit it to check if it can pass all the testing cases. As you can see, it's pretty fast and it passed all the testing cases. And the time complexity is O(n). Here, n is 10 to the power of 5. Why O(n)? Because we used the memorization. So for each of the position, it only takes O1 time. So the length of the DP array is n. So the time complexity is O(n). Thank you for watching. See you next time.